So in the last section, we saw how to compute importance scores for certain types of graphs. But as you said, that technique is not always going to work. In fact, there are two main problems that we have to deal with, and we will learn to deal with in this section. The first is this idea of a dangling node. So what exactly is a dangling node? Simply put, it's a node that doesn't point to any other node. For instance, in this graph right here, we've augmented our web graph that we had before, and we have this node 5 right here. So node 5, while it's pointed to by node 4, does not point to anyone else. There's no out degree. No out degree of node 5. It has an out degree of 0. So what this really means is that if he's not spreading his importance score to anyone, then he's going to have an importance score himself of 0. Because as we said, remember, in order for these equations to work out, nodes have to spread their importance score evenly over each link. And since node 5 doesn't spread its importance score at all, then naturally its importance score has to be equal to 0. You can also solve through this mathematically to show that P5 would be equal to 0. But basically that has a chain effect, because P5 has to be equal to 1/4 of P4 now, because P4 has 4 outgoing links. And so that means that P4 has to also be equal to 0. And then it cascades down, and it turns out that we were going to get a trivial solution, in which that all of the importance scores are going to be 0. And that's not good. So we need a way of being able to deal with these dangling nodes. But how do we do that? So if we think about dangling nodes, really, they don't really tell us much. So if a person ended up on a dangling node when he was going through this random surfing process, remember again as we talked about before, if you were on your computer doing a random surf, he would just enter some random URL into his web page. We've sort of neglected this idea up to now, and now we're going to bring it back. And he jumped to some other node randomly within the graph, possibly even his web page itself. And so what we do is we assume that the dangling node, for our purposes, actually points to all the other nodes in the graph, including itself. And so what that means is then that he's going to spread his importance score P5 5 ways throughout this network. And then basically it just becomes a problem just as before, and this will work out and we can solve for the importance scores accordingly. But there's another problem still. That's when we have subgraphs. And rather than leading to no solution, this actually leads to many solutions to our problem. And a subgraph is basically when we have more than one connected component. And a connected component is basically just a portion of the graph where all the nodes are connected, pretty simply put. If an entire graph is completely connected, then it itself forms one connected component. But in this case, we are saying that we have multiple connected components. These 3 nodes are all connected themselves, and these 2 nodes are connected as well. And they both form 2 subgraphs of the initial graph that are not connected amongst one another. And what this leads to is this leads to many solutions in the results. And so we need a way to be able to deal with this so that we can have, instead of many solutions, we want one unique solution to this entire problem. And so, how are we going to deal with that? Well, remember again, as we said before, if a person is surfing on a web page and he gets bored after a while in his process, maybe he started here, jumped up to here, went down to this node here, came back, jumped out, or whatever the web graph may look like, he would enter just some random URL web page, just as we saw in the case of the Dangling node. And so what that means is that we're going to actually bring this randomness back now, so that at any given time, we're going to assume that rather than following the web graph, that the person may just decide that he wants to jump to some random node anywhere in the network. Doesn't matter where it is. And so in order to do that, we're going to have to start weighting portions of our solution differently. So on the one hand, remember as we said before, for node y, its importance score would be equal to the importance score of all the nodes that were pointing to it, divided by the out degrees of those nodes. So if P1 points to it, divided by 0.01, P2 divided by 0.02, plus all the nodes that point to it. So basically then what we want to do is we want to actually add in some randomization component. And some component to basically say that at any given time this person may just decide to go off to some random portion of the graph. And the way that we do that is we have this portion, which we'd say maybe is called the graph portion, the graph following portion, and some weight on that, plus 1 minus that same weight, because again we want these importance scores to add up to 1, times some random component. And that would model this exactly. And that's the idea. And again, these have to add up to 1, so it turns out that this random component is simply 1 over the number of nodes. And in our example, that would be 1 over 4, or 1 over 5 if we're including that dangling node, depending. So this brings us to the general PageRank algorithm. And this is how PageRank works. So PageRank has a portion which is based upon the graph, and a portion which is based upon some random jumping throughout the network. And so basically for any of these nodes, we can start with node 1, and we'll try to write out the equation, for instance, for node 1. We have that P1, remember from before, we still have P4 coming up into it, and now we have to incorporate this dangling node in here too. So P1 is going to be equal to P4 over 4 now, because node 4 now splits 4 ways in our new example with the dangling node, plus P5, which is for node 5, over 5, because again node 5 splits and also connects to himself. And this is the graphical component that we follow, just by taking all of the integrees for node 1. That times this weight, theta, which is between 0 and 1. 0 to 1. Plus this random component, which again is just going to be 1 over 5, since we have 5 nodes. And that's times 1 minus theta. And we can write it out for the other nodes as well. For instance, we can try for node 4. So P4 is going to be equal to P3 plus P2 over 2. Let's not forget about P5 plus P5 over 5 all times theta plus 1/5 times 1 minus theta. And we can similarly write those equations for the remainder of the nodes in the network. And so, as you can probably imagine, solving such an equation algebraically can get quite difficult. And so what I'd like to show you right now is an iterative approach that you can use to solving this, which is similar in idea and virtue to the distributed power control algorithm that we saw in Q1. If you remember DPC, we had the power level at time t plus 1 was equal to the SIR at time, the SIR desired over the SIR at time t times the power level at time t. And we would iterate this over time. So we would start at t equals 0, go to 1, go to 2, all the way over. And so we have the same idea here of what we want to do. Basically, we want to keep iterating this over time, and eventually we will come and converge to the solution. And so if we denote n to be next, like for the next iteration, then we can say the next PageRank of node 1, for instance, would be equal to theta times the current PageRank of, and we'll have to write out the equation for node 1. So if we go back to our graph for a second, we saw it was P4 divided by 4 plus P5 divided by 5. So we can go back then to our iterative approach. Okay. So it's the current PageRank of node 4 divided by 4 plus the current PageRank of node 5 divided by 5 plus 1/5 times 1 minus theta. So rather than solving algebraically, we can just keep iterating through these equations to solve for the power levels accordingly. And if we wanted to write it for the second node, we have the next PageRank time 2 equal to, let's go back to our graph for a second. So we have incoming from node 1, and we have incoming from node 4. Let's not forget about node 5. So current PageRank of node 1 divided by 2 plus the current PageRank of node 4 divided by 4 plus the current PageRank of node 5 divided by 5 plus 1/5 times 1 minus theta. And that's the idea. So suppose that we start off all of the power, or sorry, not the power levels, all of the page ranks, P1 equals P2, all at 0.2, because remember they have to sum up to 1. And so let's iterate through this for each of the nodes for one iteration. And we will assume that theta is 0.85, which is typically assumed by Google in their calculations. So the next PageRank at time 1 is going to be equal to 0.85 times the current PageRank of 2, which is 0.2, divided by 4, which is the out degree, plus current PageRank of 5, which is 0.2, divided by 5, plus 0.15, which is 1 minus theta, divided by 5, since there's 5 nodes. And that'll come out to be 0.1065. We can also do this for node 2, and P2 is 0.85 times 0.2 over 4 plus 0.2 over 4 plus 0.2 over 5. Now, where did these come from? Well, this 0.2 over 4 and these other 0.2 over 4 is for the nodes that point to node 2, which we can see again from here. We have node 1 pointing to node 2, and we also have node 4 pointing to node 2, and we also have node 5 pointing to node 2. And so I believe I made a typo here, actually. Yes, this should be, 0.2 over 2, because that's for node 1, plus 0.15 over 5. And that will come out to be 0.1915. If we want to do it for node 3, go back to the graph. So for node 3, we have incoming from node 1, from node 2, from node 4, and let's not forget about node 5. So 0.85 times 0.2 over 2 for node 1, 0.2 over 4 for node 2. 0.2 over 2 for node 2. 0.2 over 4 for node 4. And 0.2 over 5 for node 5, plus 0.15 over 5, that randomization component. That comes out to be 0.2765. Similarly, for the 4th node, you can compute this to be 0.3190. And for the 5th node, you can compute it to be 0.1065. We carry out those computations accordingly. So it's pretty interesting to actually look at this if we graph this using computer software to see the importance scores over each iteration. So just like with distributed power control, we can graph this just by continually computing the importance scores over time and feeding them back in through that update equation for the next importance score. And as we see, page 4 is still the most important. It comes up to about 0.34. And eventually, these all converge, meaning they come to a unique solution, which actually solves the equation and makes it so that it no longer updates. So that the next importance score in the PageRank algorithm is equal to the current importance score. And that means that it won't update anymore. And that's, at this point, it's true for all the nodes. Then our second most important page is page 3 still, which is roughly 0.25. And our third most important page is page 2. And page 2 is about 0.174. And pages 1 and 5 actually tie here for 0.122. So this is how they go over time. And so the end result of this example, we can look at in this table over here, if we weighted them by in-degree importance, page 5 would have an in-degree of 1 from that one pointing in page 4, and this would be the ranking. First would be, again, as we said, page 3 would be in the lead. And then second and third would be pages 2 and 4. And fourth and fifth would be pages 1 and 5. We only have in degrees of 1. But as we said, in degree is really not a good way to look at importance score, because you also have to take into consideration the importance of the nodes that are pointing to the node that we're looking at. So it's important to look at the importance of these nodes pointing to node B. So when we take the PageRank into consideration, we see the order that we just saw. Node 4 is the most important still, followed by node 3, followed by node 2, then node 1, and 5 tie for last place. And this PageRank is a much better way of computing importance score. This is the way to go.